So let us look at the secant function. It is defined from 0 to 2 pi, and if you restrict it to 0 to pi, then this is the shape of a secant function. So let us try to construct the shape of a secant function that is running from 0 to pi. And as already discussed earlier on, the shape of the function is just looking like this. At the point of pi of a half, the functions of secant actually has an asymptote, and it goes to positive infinity. Then it goes to negative infinity when you approach it from the right to x equals to pi over half. So these are the restricted secant function for x restricted to between 0 and pi, and x would not be equals to pi over half. The secant function can be reflected about the y equals to x-axis. I just want to show you here roughly how would you obtain the reflections of the secant function. Let us look at the reflections again, a little bit more detail. Let us look at this point. So this point is happening at 0, 1. And then this point is happening at pi minus 1. Upon the reflections, you expect that this point to be reflected somewhere here. So you will be reflected into here, which is 1, 0. So you jot down this point, and the reflection of it must go to 1, 0. So is this point 0? This point at pi minus 1 will be reflected into a point of minus 1 pi. So minus 1 pi would somewhere here. Minus 1 pi would be somewhere here. Roughly speaking, this will be made as a reflection about the y equals x-axis. It will become minus 1 pi. So it should be somewhere here. Now my drawing is not perfect, but ideally it should be somewhere here. Minus 1 pi, which is the image of this point reflected about the y equals x-axis. You now come to the conclusion that the point here is to be reflected here. This point is to be reflected this. When x goes to pi over 2 for the left, then y goes to infinity. Therefore, this behavior is then translated into values of pi over 2 horizontally. This is values of y equals to pi over 2. As the x is approaching pi over 2, y goes to infinity. When you make this behavior on the reflection here, what you get is this curve will be reflected into the form that is starting from here, and it will be like this. This behavior that the secant x goes to infinity is reflected by this, where this is the reflections axis, so that this curve that it goes to infinity is reflected into y, who goes to pi when x goes to infinity. So that is how I will construct the reflections here to show you the curve of the inverse of secant x. Now, same thing would happen to this curve. It will goes to minus infinity when x goes to pi over 2. When you make a reflections about here, this point must go to here. So can you see how you construct the reflection of this about here? So it is like this. This is a pair that is reflected about the y equals x-axis. I can then draw the reflection, and this will be another branch of the inverse secant function. That is how these two curves is constructed. So that's all I want to say about how to construct the reflections of the secant function on the right-hand branch of the restrictions in its domain. Now the next things we have to talk about is the specific values of the arc trigonometric function. This is an example of the specific values of the arc sine and arc cos, and you have to be familiar with how this number comes about. There is also another set of chart that tells you what are the values of the arctangent is, and also another table that tells you what are the specific value of, say, arc cotangent, arc secant, and arc cosecant. Now I'll begin by defining y equals to sine theta for specific values of theta and values of sine theta. Okay, so that is easier to explain how you can construct the values of the arc sine. To understand the specific values of arc sine, it would be best to begin from the sine function, because sine function is something which is more familiar, but arc sine is something which is not so familiar. Say, for example, if theta is equals to 45 degree, when theta is, say, 30 degree, pi over 6. Sine of 30 degree is half. You can also have the sine of the other number, say pi over 3. So pi over 3 is 60 degree. Sine of 60 degree is square root of 3 over 2. We also have, of course, 0 and pi over 2. Sine 0, you got 0. Sine 90 degree, you have 1. So these are all the familiar values of sine at some specific angle. So you can actually translate this into arc sine. Say you have arc sine of x. If x is equals to 1 over square root of 2, arc sine of 1 over square root of 2 is pi over 4. The values of x in arc sine, if is 1 over 2, arc sine of 1 over 2 is pi over 6. And when x is equals to square root of 3 over 2, arc sine is an angle of pi over 3. When x is 0, arc sine of 0 is 0. When x is pi over 2, arc sine is 1. You can actually construct the values of arc sine if you know the values of sine as a function of theta. So this is a number that I construct for here. Right? So when x is square root of 3 over 2, then I am looking at this one, square root of 3 over 2. The arc sine is pi over 3, which is this number. You can easily obtain the values of arc sine for specific values of x. For example, can you tell me what is the values of arc of 1 over square root of 2, and what is the arc cos of 1? To answer these questions, one simple way is to write down the relationship. If you have y equals to cos of theta, theta is just arc cos of y. If y is equals to 1 over square root of 2, what is your theta? So you can refer to this. You ask yourself, what is the values of cos theta, so that it is 1 over square root of 2. And then you can check the table or ask Mathematica. But if you remember it well, cos of 45 degree is 1 over square root of 2, which means that the angle here is 45 degree, which is pi over 4. In other words, it says the arc cos of 1 over square root of 2 is just simply equals to pi over 4, which is just this number. These are the example that could be easily illustrated for arc cos and arc sines. Up to this point, I have just mentioned roughly how the values of the inverse trigonometric function could be calculated based on the knowledge of the original trigonometric function.